Well, hello again, everyone. Welcome to the second day of a 3-day webinar on algorithms in everyday life. For those of you joining for the first time, my name is Dr. John Lowen, and I'm a faculty member at the School of Integrated Innovation at Chulalongkorn University here in Bangkok, Thailand. The weather here today, 33 degrees Celsius, so a little warmer than yesterday. We're under threatening skies, I would say. I think thunder showers are probably imminent. Hopefully it'll cool things off a little bit. All right, we're going to continue on from where we left off yesterday, so it's day 2. Yesterday, we started with an introduction to algorithms, including a definition, some of the broad issues, and then we looked at some examples of algorithms around us and how they affect us in our everyday lives. Today, we're going to get a little bit more technical. A number of you participating in this webinar will be writing algorithms next semester. So the purpose here is to provide some perspective on the very important concepts of efficiency and of robustness. And those terms will make more sense as we move forward. And to give you some basics on how to design simple algorithms. So just to give you some foundational ideas on how to think about algorithms and how to design them. The format for today is the same as yesterday. So I'll discuss the topics for about 40 to 45 minutes. I'll ask you 2 poll questions, and then at the end there'll be about 15 to 20 minutes of questions and answers to summarize the results of the answers to those 2 poll questions, and also to endeavor to answer any questions that you may have. Okay, so let's get rolling. Day 2 then, measuring algorithms. We're going to talk about the idea of divide and conquer, and then how to design algorithms using 2 tools. So our toolbox will consist of 2 tools, Pseudocode and flowcharting. And then what we're going to do is we're actually going to write our own algorithm. So continuing on this vein of relationships and dating that we started yesterday, we're going to write an algorithm that I've called the Woo algorithm. So let's get rolling. So let's start off with sorting socks. Okay? Let's say you have a laundry basket full of socks that you need to match up in pairs. How would you go about doing it? For example, do you take out one sock, grab a second sock to see if it matches, and if it doesn't, do you throw it back in? With this method, with just 10 different pairs of socks, it will take on average 19 pulls of a sock just to find the first pair. Once you have that, it will then take 17 more pulls to complete the second. In total, to match those 10 different pairs of socks, you can expect to reach into the hamper 110 times for 20 pairs of socks. Efficient? Not at all, but it does work. So it turns out that sorting, in particular sorting socks, is a huge topic of mathematics and of computer science. With sorting, the methods used to sort, so the algorithms that you write, the algorithms that you create, may have massive differences in efficiency. And this is an important enough question to be posed on the ever useful stackoverflow.com. So the question then is, what is the best way to sort socks. And there's a number of different and interesting answers out there. So I've put a couple of the answers here. So somebody posted that the quickest is what we call constant time, or O of 1. And I'll explain this lingo as we go forward. Buy socks that are all the same. So if you have a hamper full of 20 pairs of socks, you don't have to do any sorting at all. You just grab the first 2 pairs of socks and you have a match. So that's one possible solution. Another one is what's called the bucket sort. So you sort into piles based on color, then you sort from that pile of color based on pattern until you can visually see the differences and similarities between socks and match them that way. So this is a bit of a more efficient way to sort socks. Another answer posted was the idea of a visual sort. So if you have a large enough space, you just lay out all the socks on the floor, and then humans, it turns out, are really good at seeing changes in patterns. So when you visually see 2 socks that look the same, then you have a match. So this method also actually works quite well. So put them all on a surface. While there's still socks left, find 2 that match and put them together. So that leads me to the first poll question that I have for today, which is, can you provide examples of other real-life situations where a sorting algorithm might be useful, or where a sorting algorithm you think is being used? There's quite a few of them out there. Okay, moving on. More about sorting. So in the few slides ago, I showed you some terminology. I said O of 1. There's also O of n. There's also O of log n. These are ways in which to measure the efficiency of an algorithm. And these are examples of what is called big O notation. And big O notation is a big fancy word, but it's actually a simple way in which to measure the efficiency of an algorithm. And it classifies algorithms based on what's called a worst case scenario. So what do I mean by a worst case scenario? Well, I'll show you some examples as we move forward here. Basically, it's how many operations does it take to get the desired outcome from that sort. So to retrieve something if we're doing a search, and to have our items that we want to retrieve from our sort. So big O notation, the advantage of it is that it omits the fine details, and mathematicians might say, oh, the horror of it. Details are the most important thing. But basically, it divides problems and their algorithmic solutions into what we call broad classes. What are those classes? We're going to take a look at a few of those classes in a minute here. And again, like I mentioned just a minute ago, big O notation, with big O notation, each class represents what we call the worst case running time. So basically, what is the slowest speed that this algorithm could possibly run? So what is the worst case scenario of this algorithm? So there are some broad classes for big O. And what I put in here is a chart that shows the complexity of big O. And in this chart, we have on the y-axis the number of operations that need to be computed. And on the x-axis, we have the number of elements that are part of this algorithmic operation. So for example, if we're doing a sort, we might have 50 words or 50 numbers. That would be the number of elements. And then the efficiency of the algorithm would be determined by the number of operations that we would need to complete in order to sort those numbers. So the broad classes are constant time, big O of 1, logarithmic time, which is big O of log n, linear time, which is big O of n, quadratic time, which is big O of n squared, exponential time, and then also factorial time. So what I'm going to do is I'm going to actually go through a very simple example in a minute that shows you how constant time, logarithmic time, linear time, and quadratic time would work in an algorithm. Here I've just put a table in to give you an idea of how each of these classes works in regards to efficiency. So you can see on the left-hand side of this table the big O notation for O of 1. Now remember, this was the example where we had all the same socks. So it doesn't matter how many elements we have or how many socks we have, we're going to find a match with the first one or the first pair that we grab. Okay? You can see with O of log n and O of n right up to O of n factorial that as we add more elements, you can see the number of computations or the number of operations that we need in order to complete the task becomes quite large. So from this table, you should get an idea of what type of algorithm you are endeavoring to aim for in regards to the efficiency. Okay? All right, so let's take a look at some of these different classes by using a simple example. Okay, so the example is we have a class of 16 students. Okay, and when I was leaving the classroom, one of the students grabbed my phone and they hid it. Okay, so the scenario is student hid my phone. As I was walking out of the classroom, I actually saw who grabbed it and hid it, so I know. So the approach is O of 1, because when I come back to the classroom, since I know that this person, Tiger in this example, hid my phone, I'll directly ask him to give it to me. So I go up to Tiger and say, hey Tiger, please give me my phone. That's one operation. So the worst case scenario is it takes me one question to find my phone. So as you can see, this is actually a very efficient example of an algorithm that solves the problem and produces the output from only one calculation is highly desirable. So an algorithm takes the same time to execute regardless of the amount of data. So it wouldn't matter if there were 100 students in that classroom or 1,000 students in that classroom. If I saw that Tiger took that phone, I would only have to perform one calculation in order to retrieve my phone because I know who it is. Okay, so that's an example of O of 1, constant time. The second example of who hid my phone is in linear time. Okay, so with this scenario, I walked out of the classroom and I didn't see who took my phone. Only the student who took my phone knows about it, so none of the other students saw either, so none of the other students know. So what I'll have to do when I come back, if I want to find my phone, is I'll have to start in the front row and I'll start to have to ask each student in that classroom out of 16, do you have my phone? Okay, so in the worst case scenario, I'll have to ask n questions. So n in this case would be 16 students. In the example that I've shown here, it turns out that Tiger is the 11th student that I asked, so I had to do 11 computations in order to find my phone. But the worst case scenario in this example would be if Tiger is the very last person that I ask. So he's the 16th student that I asked. So therefore, the worst case scenario for this example of O of n would be 16. Okay, so the idea is when we classify the algorithm, we classify it according to the worst case scenario which is what is the efficiency according to, in this case, the last student that I would ask. It may be that Tiger is the first student that I ask, but that's not the worst case scenario. The worst case scenario is if he's the last. Okay, so that's an example of O of n. So that's what we call linear time. The next I want to look at is quadratic time, and this one becomes a little bit more complicated. So the scenario here is a little bit different. So in the entire class, only one student knows in which student's bag my phone is hidden. Okay? So the idea here is I have to find out through each student who the student is who knows where my phone is hidden. So my approach is I'll start questioning each student individually. Okay? So I'll go to student 1 and I'll say, do you have my phone? If they say no, then I'll say, is it in student A's bag? Is it in student B's bag? Is it in student C's bag? So basically, for each student, I have to ask 16 questions. So for 16 students, that's 16 questions. So in the worst case scenario then, I'll have to ask n squared questions, or 16 times 16 questions. So if Tiger is the very last student that I ask from the very last student, in other words, then the worst case scenario would be 16 squared, which would be 256 computations or operations that I would have to perform in order to find my phone. In the end, if my phone was in a student's bag, then the algorithm will have accomplished what it was set out to do, which was, let's find the student who has my phone. So it worked. The algorithm would be considered to be successful from a practical perspective because my phone was found, but not very efficient. Okay, so that's O of n squared, quadratic time. Next, the last one I want to take a look at is a little bit different. It's O of log n, or logarithmic time. So a bit of a different scenario here. Here, all the students, so all 16 of them, they know who has my phone. But they'll only tell me if I guess the right name. So what is the quickest way, what is the most efficient way that I can find out which student has my phone? So what I'll do with O of log n is I'll first divide the class in half. So I'll have 8 students on one side and 8 students on the other side. And then I'll ask, is my phone on the left side or the right side of the class? And because all students know, they'll know. Then, once I know which side of the room my phone is on, then I'll take the class again and I'll divide it in half. And then I'll ask the same question. Is my phone on the left-hand side or is it on the right-hand side? Students will answer. Once I know if it's the left or the right, in this case it would be the left, I'll ask the same question again. Okay? So then, at the end, I'll be left with just one student. Okay? So the worst case scenario with O of log n is that I will have to ask log of n questions, or in this case 4 questions. Okay? So that's an example of O of log n. So this leads us to the idea of divide and conquer. So it sounds like the purpose of a video game, but it turns out this is actually a terrific strategy when thinking about how to optimize an algorithm. We saw this earlier in the who hid my phone example. So merge sort is a legendary algorithm that uses this concept, the idea of log n. Basically, each pass has the items, sorts them, and then merges them back together again. Oops, sorry. So to completely sort n items, you'll need to make as many passes as it takes for the number 2 multiplied by itself to equal n. Well, you might at this point be going, huh? That's a little bit confusing. So let's take a look at an example, searching in a dictionary. So the English dictionary has approximately 160,000 words in it. So we've decided that we want to look for the word optimization. We're not quite sure the definition of optimization. So we have an actual physical dictionary in front of us. And we want to search and sort using the divide and conquer method. Okay? What is your strategy? So do you start from the beginning of the book and read each word from that point? So start with aardvark, abacus, etc., as you're moving forward. That method will work. That would be considered to be O of n, or linear time. But we know that O is somewhere near the middle. So what we can do is open the dictionary. So our first operation is to open the book to the middle. And then we can see where we are. Okay? So if you're being efficient, then you should be exactly in the middle. And then you can look at where you are, and you can either go to the right or to the left, depending on where you open the book. So let's say you opened on M. Now you've opened on the letter M. Now you've eliminated half of the dictionary because you know O will be to the right of M. So basically what happens is, every time you divide and conquer, you have half the number of pages or words left that you need to search through. So it turns out that if you're efficient with O of log n in this example, it should only take you 17 operations, worst case scenario, to find the word optimization. So that's a lot more efficient than, say, using linear time, O of n, where O would be about, I'm guessing, maybe 100,000 words into the dictionary. So that would be 100,000 operations that you would have to perform instead of just 17. So I hope you get the idea that the divide and conquer method, when you're searching and when you're sorting, is very, very efficient method to use. Okay? Another place where you'll see O of log n, so if you do have a bit of background in computer science, with a binary search. So let's say that the nodes at the bottom level represent items in some sorted collection. So if you had 16 to start again, it would take only 4 operations, just like we saw with the example with Tiger hiding my phone. It would only take 4 operations to find what you're looking for, assuming that those 16 values are already sorted. Okay, so the idea of O of log n, divide and conquer, is very, very powerful when you're talking about searching and sorting algorithmically. So where do we see this in everyday life? Well, an example of sorting is done in sports. So if you're a sporting person, you're interested in sporting events, sports tournaments are based off of algorithms. It's all about numbers, right? So tennis, badminton, basketball, football, they all have some sort of algorithmic method for finding out who's the best team, who's the worst team, and to determine some sort of ranking. And they do this a bunch of different ways. The first one I want to look at here is the idea of a single knockout. So a single knockout tournament is quite similar to this binary sort that we saw on the previous slide. So the idea is that you pair off 2 participants, whether it be 2 teams or just 2 individuals, and the winner stays in the tournament and moves on, and the loser is knocked out. So basically, for each round, you have the number of participants. So the advantage of this is that you can include lots of participants for relatively few rounds. So where you see this in prominent tournaments is like the Grand Slam of tennis, where you have 128 participants to start, and it only takes 7 rounds or 7 games for each participant who wins to get to the final, where they will determine the overall winner. So we can have lots of participants in a small number of rounds in a shorter period of time. The disadvantage of this, of course, is you lose 1 game and you're out. So if you have an off day, there's no way to redeem yourself, even if you are statistically better than the person that you played. Another form of sports sorting is the round robin tournament. Now, this is an example where each team plays all the other teams once. So where you would see this is in many sports leagues. The EPL, the English Premiership. In the US and Canada, you would see it in hockey and basketball, in baseball. So each team plays all the other teams once or more than once, depending on how long the season is. The advantage is that it's a better indication of the best team. You can have an off day, yet statistically you may be better. You can have an off day, and over time you should still end up with a better record and then be ranked as the better team. The disadvantage of this, though, is that more teams means exponentially more games. So you fall towards that dreaded O of n squared, or quadratic efficiency. So you have to play a lot of games. So with sporting leagues, their season, where they play the round robin games, will be extended out over a long period of time, sometimes a matter months and months. But the difference in the number of rounds that needs to be played, again, with 128 teams, you only need 7 rounds, and you've made it to the last 2. With 8 teams in a single knockout, that's 7 games total. For round robin, it's a significantly increased number of games. And you can see there it would be a total of 24 games, or 24 operations, if you want to call it that, to find out who the best team is that's ranked at the top. Okay, a couple more. Ladder tournament. This is an example of the infamous inefficient bubble sort. So if you talk to mathematicians and people who write algorithms for a living, they'll tell you that bubble sort is incredibly inefficient and really has no practical use anywhere. It turns out that it does with a ladder tournament. So all participants are in a ladder, like you can see on the right-hand side of this slide here. And a participant who's in a level below can play a participant who's in the level above, and vice versa. And if they beat that participant above them, they would move up and that participant would move down. So basically, if you're better, you're going to bubble up or move up to the top of the ladder. It's often used in places like combat sports. So Muay Thai, MMA, boxing, where you're ranked, and if you want to move up the rankings, you have to take on somebody who's above you, or square off against somebody who's above you, and if you beat them, then you'll move up in the rankings. So the bubble sort does have its use. EPL, which I mentioned earlier as a round robin, is round robin for the regular season, but then once they've determined who the best and the worst teams are, the poor worst teams have to go into a sort of a ladder competition or a bubble sort in order to decide and to determine who gets promoted from the division below and who gets relegated down to the division below based on how they compete against each other. So theoretically, a team from the lower division can bubble up, and a team is then relegated and bubbled down to the division below. So that leads us to this concept of robustness. So with big O, we talked about efficiency, but efficiency doesn't necessarily mean robust. Okay? So as we've seen, the single knockout is incredibly efficient, right? We can get rid of a whole bunch of participants very quickly in the form of a log n efficient algorithm. But how robust is this method? What do I mean by robust? What I mean is are we actually finding out who the best player is? Does this algorithm find the best player? So let's do a little bit of math here. So let's say we go 7 rounds. So in single knockout, that means we're down to the last 2. If we go 7 rounds, if we have a player or a participant who's predicted to win 70% of the time, so they are significantly better than the other participants that they're going against, how often does the best one win? Well, it turns out at a 70% success rate, only 8% of the time. So what about that other 92%? So it turns out that this single knockout algorithm is very efficient, but it's not actually very robust. So if we go back to the Grand Slam analogy, let's talk about one of the best male tennis players of all time, Roger Federer. He had a Grand Slam record of 362 wins, 59 losses. That's an 85% win record. So theoretically then, he should win 85% of the time. So if out of 128 players, we apply this winning rate, he has a 32% chance of winning. In actual fact, he has won 20 of 79 Grand Slam tournaments, so that's at a clip of 25%. So this math actually holds true. So maybe we could say he has slightly underperformed at Grand Slams, which is quite an interesting thing to say about probably one of the, if not the best male tennis player of all time. On the other hand, a single loss in bubble sort doesn't move a team or player out of the competition. It just bubbles them down one. So all they have to do is play more games and win more games to bubble back up. So it turns out actually that bubble sort, which mathematicians say has no redeeming qualities, turns out that it's way more robust than a single knockout tournament. Okay? So the idea here, what I'm trying to get you to think about, is the idea that an algorithm's efficiency isn't the only measure. We can also measure an algorithm based on its robustness, or how good does it produce the outputs that we are desiring to accomplish. And it turns out that Grand Slams are single knockout, but if we look at the year-end rankings, the year-end rankings are a more true indicator of how good a tennis player is. So if we go back to poor Roger Federer, who has underperformed in Grand Slams, Federer is on only 25% of the Grand Slams, but in the past 17 years, at the end of the year, he's been ranked in the top 3, 15 of those years. So obviously he's one of the best players. The other 2 years he was actually injured, so I don't know that they even count. So again, what I'm highlighting here is the idea that single knockout, yeah, we can have a lot of players and we can get to a champion quite quickly, but maybe not the most robust way to figure out who the best player is. All right. So that leads me to poll question 2. What are some other important considerations when designing an algorithm? So what are some other things other than robustness and efficiency that you can think about? Okay, so with that poll question, just put a 2 in front of it if you have something you want to post, and then the lovely Dr. O beside me is again today compiling your responses, and she'll provide me a synopsis for the Q&A. All right, so now that we have an idea of the important things about algorithms, how do we actually design one? Let's go ahead and build up a foundation on how we can accomplish this goal of actually designing a simple algorithm, which we're going to do. Remember, an algorithm is a plan for solving a problem. And so we have a finite set of instructions. So an algorithm, in order to be considered an algorithm, must go through some calculations and produce output at some period of time. Some algorithms, again, more efficiently than others. So it's finite. And it accomplishes a particular task, which are outputs. So for the basics, 5 main steps. Get a description of the problem, analyze the problem, so think about it, of course. Develop a high-level algorithm, so more on this in a sec. That's part of our toolbox. And then refine the algorithm by adding in more detail. So this is the idea we talked about yesterday of the maturity of an algorithm. As you're designing an algorithm, you test it, and you refine it, and you test it and refine it. You iterate until you have something that you're hopefully quite proud of and that is efficient and robust. And then review the algorithm, go through that process again and again. So that's the idea here. So let's take a look at an example. So let's go back to the dating thing. Say you have a crush on your classmate. Okay? Crush means that you like them, you're attracted to them, you want to ask them out on a date. So in this example here, I've proposed 3 algorithms. Okay? So remember, 3 main parts to an algorithm: that it's finite, that it has a set of instructions, and that it accomplishes a task or an objective, so it produces outputs. So the first algorithm here in this table is pretty simple. The inputs are you and your crush. Okay? And the process, the algorithm, is a very simple algorithm. For you, it's O of 1. Basically, you go on your line or on your messenger or whatever messaging tool you use, and you message your crush and you say, hey, do you want to go out on a date? But what happens is their response is no. Okay? So you go back to your boring life, unhappy, the dream is over, but it was quick. It was a quick algorithm. It was big O of 1 message. Okay? But you're not happy. So you go back to the drawing board. And you decide, okay, let's design a new algorithm that's going to have the desired output of yes. So what does that algorithm look like? Well, it's more complex because you have to do what we call a bit of wooing. Wooing means get his or her attention. Do some things that make them more interested in you. Okay? So your algorithm then that you decide on, and this is just arbitrary. You can plug in any values you want here. We're going to do this over 30 days. So we're going to take 30 days to woo. Okay? So we're going to chat online for a month. So we're going to go online application or whatever messaging tool. And every day you're going to chat and you're going to get to know each other. Then once a week, you're going to see them. These days in COVID-19, maybe it has to be a Zoom call. So you do a Zoom call once a week. So once a week during these 30 days. And then also, you want to meet the parents as part of the process. So maybe you can get their approval so that she or he is more willing to say yes. So, and then at the end of that 30 days, your algorithm says, okay, let's ask him or her on a date. Okay? So that's your algorithm. So the algorithm, then you go through that process and wow, the answer is yes. So your algorithm was a success. So you patent it, you market it, you sell it, you make a bunch of money and you retire young, or not. So this algorithm has more complexity, but it's still only linear. It's only O of n. So we have n set to 30, right, 30 days, and we loop through day by day, right? And we perform the tasks that we need to perform within that 30 days, and then at the end, we ask for the date. So it's finite. It's 30 days. So our n is 30 in this example. Okay? Now, you're designing algorithm 2. So let's say that during this process of designing algorithm 2, You diddle and you dawdle. She puts you in, or he puts you in the friend zone. Okay? So now you're in the friend zone. Now you're in what would be considered an infinite state, or an O of infinity. Because you're a friend, it doesn't matter what your algorithm is, you're never going to get a data out the other end because you're just a friend. Okay? So that's the idea of finite versus infinite. If you're not in the friend zone, then it's finite. You still have a chance. You can still process through an algorithm. But if you're a friend, then it becomes infinite and you're out of luck. So no matter what we do with the algorithm, we will never get the desired output of yes. So that's another idea that we should be considering here. Okay, so now let's say you diddled and dawdled. You took too much time. Well, now algorithm 2 is no longer in play. You're stuck with algorithm 3. So what is happening here with algorithm 3? It's become much more complex, as you can probably tell. All right, so what happens is, in the time that you've spent doing nothing about this, 2 of your classmates have also developed a crush on him or her. So this means that you're now confronted with a way more complex algorithm. You may need more time. You may need more money. You may need, well, you certainly have an elevated level of stress. So there's more stress involved here. So what these have done, what's happened here, is your time and your space complexities of your algorithm have increased. Okay? So again, your algorithm has become much more complex. You may need to send flowers. You may need to send chocolates. You may need to write poems, love letters. All of these things take time, and they're stressful, and they're costly, potentially. And you also need to make sure that you're doing a better job than the other 2 classmates who are also in this process of wooing. So who knows how complex this algorithm will get? It may creep towards the dreaded quadratic O of n squared, because we have so many things that we have to do in order to get our desired outcome, which is, of course, he or she says yes. So that's the idea here, is that depending on the inputs and what our desired outputs are, the complexities of the algorithm can become quite, the intricacies can become quite complex in your algorithm. Okay, so what we need to do then is that we need to quickly write this algorithm 2 so we don't get stuck with algorithm 3, because algorithm 3 is highly undesirable, right? So let's get down to the basics here and let's get algorithm 2 written. So this is what we're going to do. We're going to write algorithm 2, okay? So as part of our toolbox, there's 2 common methods that we can use. We can use pseudocode, which is just a way to write out in English language. It's a complex word for a simple thing. We're going to write out our algorithm in simple English language. The other option is a visual method, which is flowcharting. So we can make a visual diagram of the decisions and processes for that algorithm. And these 2 processes, pseudocode and flowcharting, they don't require any knowledge of any computer programming language. In fact, quite often when you go into computer science, you'll learn how to do these things before you actually get into any serious coding. Okay? So how do we create it? To start with, let's look at pseudocode. And it's just a fancy word for writing out an algorithm in plain language instead of code. There's no very specific standard. There's some rules we can follow, but there's no general standard for syntax. So we don't have to follow any strict syntax. So people ask me sometimes in coding class, in programming, is this good pseudocode? And as long as it explains your problem well, then it's probably okay. Varies in style from author to author. However, there's some basic structures you can use that are very useful. And I've listed 5 of them here. So we have the sequence. So what that shows is just one step after another. If then else. Now this is the logic. Okay, and our algorithm 2, our woo algorithm, is going to use a little bit of logic. Okay, so we're going to use if then else. We also need some sort of loop, right? So remember, our number of operations will be 30 days. So over 30 days, we're going to perform a bunch of different tasks in our algorithm. We're going to send line messages. We're going to Zoom once a week. And after 15 days, we're going to meet the parents. Okay, so these are statements that we can create using logic, like if then else, and then also we need to put that in some sort of a loop. And in our case, we're going to use a for loop. So the two out of here that you'll see in the next slide are the if then else statement or if statement and a for loop. Okay, so let's take a look at it. So pseudocode for our Wu algorithm can look something like this. Okay, so this is algorithm 2. So what you see here is the pseudocode for going 30 days and performing some tasks in order to get our desired output of yes. So you can see there, the for loop says for day less than 30. So while we're counting up to 30 days, so day 1, day 2, day 3, day 4, day 5, we're going to do some tasks. The first of those tasks is we're saying if we get to the end of the week, so if day is greater than 7, because we're counting our weekdays, then we're going to do a Zoom call. Okay? So our algorithm will automatically initiate that Zoom call and we can chat with our crush. Then what we're going to do is we're going to set the day back to 0 because we're starting a new week. Okay? So that's the logic in our algorithm for our Zoom call. Next, we're going to look for day 15, because once we get to day 15, we're going to go hopefully meet the parents and they'll say, oh, yeah, he or she, they're awesome. Great to meet you. And you can continue from there. And then you'll see there, there's a statement that says send line message. We're going to do that every day. So we just put it in there as a statement, send a line message. We're chatting back and forth. We're getting to know them. And then you see there, the second last line says end for. So once we get to day 30, we're done that loop. Then after day 30, we initiate our date request. Okay? And then because we've gone through this algorithm successfully, we're hoping that the output to that is yes. But that's not up to us. That's up to him or her. But we're hoping that this algorithm breeds success. The other way we can design our algorithm is using flowcharting. Okay? So flowcharting is used to show the logic and process for your algorithm. And there are some basic shapes that we see here on the right that may be used to indicate the flow for your algorithm. So we have a start and we have an end. And in between, we provide some inputs. We have some processes. We have some decisions to make. Decisions would be our logic, so synonymous with an if, then else statement. And then we have an end. So we get, at some point, remember, because an algorithm is finite, we're going to get to the end, where our algorithm has completed and our outputs are available. What you see on the bottom here is an example of a flowchart, a plastic flowchart template. So I'm old enough that when I did my undergrad back in the early 1990s, part of our required course material for programming was a plastic flowchart template. So I had to go to the bookstore and buy it. And we did all of our flowcharting for our algorithms using a paper, a pencil, an eraser, and a piece of paper, and this flowchart template. These days, it's all done through software. And there's some really good software out there, like Microsoft Visio, for example. So here's what our flowchart would look like. So this is an example of the Wu algorithm flowchart. And you can see there in green, we have a start point. We set our inputs. So we set our data 1 and our week data 1, because remember, we're going 30 days. And every 7 days, we want to do a Zoom call. Then you see a diamond there. That's called a decision diamond. And it says day less than 30. So from that, if the answer is yes, it means we haven't reached day 30 yet. So we need to keep continuing through our algorithm and see if it's the end of the week to do our Zoom call. See if it's day 15 to meet the parents. And then we loop back. And we keep on looping, remember, until n is equal to 30. And then once n equals 30, then where it says day less than 30, we'll hit the n, which means no, it's not less than 30 anymore. We've hit day 30. Then we can initiate our date request. Okay? Then the output of that, of course, is hopefully that, our fingers crossed, the date response is equal to yes, and then we are at the end of our algorithm. So our Wu algorithm worked successfully. So from a simple crush, basically, you've created a template using flowcharting and the logic using pseudocode for writing an algorithm that will successfully get you a date. Now, the next step, of course, would be to write the actual algorithm code. using a programming language. So for example, Python. And what I've done is I've just gone ahead and written this simple algorithm, and all it does is it prints out statements. But, and I've called it the WOO algorithm. I haven't patented it yet. Even without knowing Python, you can see the basic structure of the algorithm pseudocode. So for the loop, the for loop is on line 5. The weekly Zoom call is line 6. So that's our if statement for our Zoom call. And then our if statement for meeting the parents on day 15 is on line 10. So here's the simple Python code, or the Python code for our simple algorithm. So you can see there line 5 is saying as long as it's between day 1 and day 30, so we're still wooing, so we're still in the state of woo. We're Zooming, we're meeting the parents, we're sending line messages. Once we get to the end of, you can see line 15 there, we're finished our wooing, then we can say, all right, time is up. Let's ask him or her out on a date. Hopefully they say yes, and our algorithm is successful. All right, so that's the process for taking an idea, thinking about it, generating some logic, and then putting it into practice with some actual Python code. So that's all I wanted to say today. I hope that's been everything that I've said has been fairly clear. So just to summarize, our final thoughts today, we looked at ways to measure an algorithm, so big O notation, and just a broad stroke. Don't panic about the concept if you don't understand it. Just go back. There's lots of information online about big O notation, lots of good examples of big O notation. So if it's not clear, you can go and take a look online at all the great resources. We also solved a problem using different algorithms to show efficiency. So using the who hid my phone example. We used pseudocode and flowcharting to create the WOO algorithm. Yeah, and hopefully you found that process useful of actually stepping through and thinking about it. So tomorrow, we're going to look at qualitative versus quantitative. So this is more my area of research. So more knowledgeable in that area. Of course, any discussion about algorithms these days wouldn't be complete without putting some relation in between algorithms and COVID-19 in there. So I'll look at some examples of how algorithms are useful with COVID-19, and hopefully you'll find that very informative. All right, so that's it for me talking. Let's move on then to the second part of this, which is the responses and questions section. I'm just going to take a drink of water. Okay. Okay. So the first poll question was, just to summarize again, examples. What are some examples of other real-life situations where a sorting algorithm might be useful? I've got here, again, Dr. O here has given me a list. Finding a person in a crowded place. Yes. Now, these days, that can probably be accomplished through some facial recognition software, or before masks. There are other ways, like gait analysis, for example. So we can use algorithms to find people in a crowded place, employees in a company, colleagues at a workplace, also enrollment in school. Yeah, there's a process to that. So yeah, I mean, so if the software that's used by the enrollment team here, probably it has some algorithms built in where it automates a bunch of the steps that need to be taken. Oh, sorry, I'm looking down at my computer. The steps that need to be taken for getting students through all the process, like registered in classes, registered in events, all of that sort of thing. So yeah, for sure, some algorithms to for enrollment in school. Demographic systems, yeah, absolutely. Anything where you've got mass amounts of numbers, right? Finding race, finding age, finding sex, for sure. Somebody says they're off to sort some socks. Don't pick them out one by one. You'll frustrate somebody around you. That whole thing came from a student at Harvard who was in, I think he was in engineering, and he had a roommate, and he constantly watched his roommate sorting socks that way, and it drove him bonkers. So yeah, interesting example. So that's for sort algorithm examples. I had a couple here that I listed as well. Lists. Human beings are fascinated with lists, right? Like we see these lists everywhere. Fortune 500 lists, best universities lists, top airlines. We love to sort things and rank them, right? Google, TripAdvisor. So lots of different sorting algorithms out there. Alternative. Okay, I'll get to that in a sec. Okay, so that's poll question 1. Poll question 2. What are some other important considerations when designing an algorithm? Was that here? Oh, okay, there. Yeah, I see. Effectiveness. Yeah, effectiveness. So you can have, that's a really good one. You can have a highly efficient algorithm that's highly robust, but are the outputs actually what you want and what you expect? So it is possible that the person who wrote the algorithm wrote it according to the specifications and made it incredibly quick, but that it doesn't solve the problem. So it's not effective. That's actually quite common, right? So when a person or a team is assigned to write an algorithm, the algorithm they write is as only good as the information that they have about it. And it's quite possible that the information might have been incomplete or inaccurate. So the algorithm, in their mind, does what it's supposed to and it does it quickly, but it's not effective. So yeah, that's a really good one. When inputs are rounded up or down, it may produce unexpected output. Yeah, that's a good example. Accuracy. So accuracy and effectiveness. Again, yeah, accuracy and robustness are similar. But effectiveness, yeah, also outlier data. So, I mean, like, when you're dealing with big data, as an example, outlier, a lot of the process of sifting and sorting through big data is actually cleaning it. So again, then if you run an algorithm off of that big data, it's only as good as how good the data has been cleaned, as an example. So somebody's saying outlier data. I think that's maybe kind of similar. Precision. Yeah, somebody said about rounding up and rounding down. Have to consider time. The more inputs, the more accurate will the algorithm be. Yeah, time and space complexity. We didn't really talk much about it today. We could have. We didn't have a lot of time, but algorithms are about time and space. So that algorithm 3 was interesting because it introduced more complexity. So it increased the amount of time probably needed and the amount of space needed for that algorithm to execute. We didn't know exactly. We didn't define that exactly. But the idea was to get you thinking about that idea, right? Where the more inputs we have and the more data we have to massage, the more complex our algorithm becomes. And that might be unavoidable, right? That might be unavoidable. Okay, so I think that was all from poll question 2. So what's some important considerations in design? Some comments. Somebody said we have an alternative algorithm. So if you have a Lamborghini, then you'll definitely have a higher chance of yes. Yeah, that's a possibility. Somebody else said meet the parents. Isn't that too quick? I was talking with Dr. O about this before this webinar, and I'm not an expert on 19 and 20-year-old dating in Bangkok, in Thailand. So I just kind of threw those variables out there. But of course, let's say that I was writing this algorithm as part of my startup, and I wanted to write a really good algorithm. Of course, what I would do is I would actually probably poll, starting with all of the students in the School of Integrated Innovation, because they're the ones who would actually use this algorithm, and they would have a much better idea of what sort of things I should include in my algorithm. And maybe meet the parents wouldn't be one of them at all. Okay, I can't say that one. Meeting the parents is a remarkable act of generosity, but not a necessary prerequisite for companionship. Yes, no, not at all. I agree. I'm getting the sense that maybe I should take that one out of my algorithm if I am going to put this into production. And in your opinion, which algorithms would be most affected? Oh, I'm not an expert in that. I can't answer that question very well. I'd have to defer. If I had another expert here, I would defer to them. which algorithms would be most affected by quantum computing? I actually don't have enough knowledge to answer that question. How are we on time? Okay. One question that I just wrote down a couple, I think that's all the questions I have. So I just wrote down a couple of questions that I thought might generate some thinking. Which is a better method to know, pseudocode or flowcharting? I thought that would be something that might be useful to know. Flowcharts are easier to create, particularly if you have a good tool, like I mentioned, Microsoft Visio. They also provide a good visual representation. Some people are just visual. It also provides a higher level of abstraction. So flowcharting is often used when you're first thinking about a problem and you want to get it from your brain into some written form. So it's good for higher level first. And then once you have an idea at a higher level, then what designers will often do is they'll then move to pseudocode. Because what pseudocode does is it bridges between that high level of abstraction and gets it closer to what it would look like as code. Right? So the pseudocode acts as a bridge between the flowcharting and the actual programming, say in Python or Java or whatever language. So which is better? I mean, it depends. If your algorithm is fairly simple, the research that I was doing the last few weeks, if your algorithm is fairly simple, what a lot of people are doing these days is they just skip flowcharting and they go straight to the pseudocode because that'll provide enough information. Pseudocode is also easier to follow for someone who wants to step through because it's sequential logic. So it's a bit easier to understand. If your flowchart is too big, it might be very, very difficult to follow. So again, use it as a higher level of abstraction. Another question I put was, everyone has their own strategy for sorting. How do we know which one is best? Now, this goes to the idea of balancing between efficiency and robustness, right? But it probably depends on your desired outcomes. And examples with databases. So databases, they have a good strategy for sorting. If you have a field in a database that you're going to search through a lot, what you can do with a database is you can index it. And what that does is it makes the query or the retrieval of information from that field much quicker when somebody wants to actually access it, because you're dealing with data that's already sorted. And data that's already sorted is much easier to search through and much quicker, more efficient to search through than data that has not yet been sorted. And the last question, I think we're just about at the end here. How do we know if our algorithm solution is the best method, right? So what I'm guessing I'll see, and what I have seen in the past with students who come to me with an algorithm they've designed is how do I know this is the best way? The first thing it should do is it should solve the problem. Okay, so the first thing it needs to be is robust. Okay, then what you can do is you can work on efficiency of that algorithm. So I've solved the problem, but are there better ways in which I can solve that problem? So first be robust, and then work on efficiency. That would be a useful path to follow. Okay. Other variants of algorithms for sporting events. I think I've got another minute or two. Other variants you see, those of you who are interested in sports, the double knockout. So still fairly efficient, like the single knockout. But if you've had a bad day, maybe you're a participant and your daughter kept you up all night. You didn't get any sleep and you lost because you were exhausted. The double knockout gives you an allowance for one bad game or one bad day. And the World Cup of Football is an interesting one because it's another good example because it uses two different algorithms in finding out who the best team is. So those of you who follow the World Cup of Football, you're probably thinking, oh yeah, right. The first thing it does is it does a round robin in groups. And so you find basically, I think it's the best these days, it's the best two teams out of a group. And then the bottom two are then eliminated. So the best teams come to the top in round robin, and then the 16 teams that are left, they actually go into a single knockout. So it's balancing this idea of efficiency, so doing it over a short enough period of time. I think the World Cup happens over a month, with the idea of also wanting to find the best team. So being robust balancing the idea of robustness and of efficiency. Okay, I think that's all I have on my agenda here. So I think our time is also up. So thank you very much for listening. I hope it all made sense to you. Please tune in tomorrow for day 3, where I'll talk about some qualitative approaches to writing algorithms, and also a discussion about algorithms as they relate these days to COVID-19. So yeah, hopefully we'll see you all then. Please tune in 1 o'clock Bangkok time tomorrow, and we'll see you then. Bye-bye for now.